Before we get started on the 2 to 4 decoder tutorial, I need to explain why RF is used over traditional logic wiring. We all know this, the classic OR gate. If either input is true or both are true, the output is also true. Now, if we want more than 2 inputs using standard OR gates, we have to stack them in a tree. For example, 4 inputs require 3 OR gates. That means for a signal to reach the output, it has to pass through 2 gates, or as I like to call it, 2 logic layers. If we want even more inputs, we just keep stacking gates. More inputs means more depth, and that depth adds more delay. This is where RF becomes useful. Over here, I have multiple switches, each connected to a broadcaster. All of these broadcasters are set to the same frequency as the single receiver. That receiver effectively behaves as an OR gate for all of them. And here's the important part. There is no limit to how many broadcasters can transmit to that one receiver. That means we get an infinite fan-in OR gate in a single logic layer. Now, to turn this into something truly powerful, we simply add a blocker or any NOT condition to the output of the receiver. Now, we've turned our infinite input OR gate into an infinite input NOR gate. And NOR gates are special. They're universal gates. That means we can build any logic function from them, such as AND, XOR, or anything, including what you've all been waiting for, this decoder. Alright, to start, this row of broadcasters here is bit 1, and this row here is bit 2. You can see that on the signs. Each bit has 2 frequencies assigned to it, one for when the switch is on, and one for when it's off, which is just the inverted output. For bit 1, we assign 100 for the normal output, and 101 for the inverted output. For bit 2, we assign 102 for the output, and 103 for the inverted output. So now we take these 4 frequencies and apply them over here. Each of these receivers is assigned one of these values in a very specific pattern. If you look at the sign, The pattern is simple. For bit 1, we go on, off, on, off. For bit 2, we go on, off, off. That pattern isn't random. We're building the truth table. Since we're using NOR gates, here's what that means. Look at the first row. Both bit 1 and bit 2 are set to their on frequencies in that row. Because this is a NOR gate, the only time it outputs a signal is when both switches are actually off. As soon as we flip either switch, that row loses its match and the NOR shuts off. So each row is basically waiting for one exact combination of the switches. Now, once those patterns are assigned, we give each row its own frequency for the broadcasters. These rows act as the inputs to our OR gates, which, like I showed earlier, are just receivers collecting broadcasters on the same frequencies. Then, we take the output of that receiver and run it through a blocker to invert it, turning that OR into a NOR. With every frequency assigned and wired, we can now test it. Each switch combination should light exactly one output. And there you have it. To scale this, it's really as simple as just doubling the pattern each time you add a new bit. For example, adding a third bit means you just double the pattern of ons and offs. I hope this helps to understand how I built this gigantic decoder, which will be the backbone for the fair adder. If you have any questions or any requests, leave them in the comments, please. Subscribe for more.